So coming to the theory of plate tectonics. So continental drift hypothesis, it paved way for a new theory which was known as plate tectonics. So now what happened in plate tectonics was that after the Second World War, there was a lot of exploration of the seafloor, and especially by the US Navy, there was a lot of exploration. And why was this exploration happening was because after the Second World War, they were basically looking for the live mines that might still be present on the ocean floor. Okay, so while they were in the process of looking for those live mines, they happened to map the ocean floor. And what did they observe? They observed that some portion is higher than the surrounding ocean. It is 2 to 3 kilometers higher than the surrounding ocean, and this part they termed it as ridges. The term ridge here is a misnomer. Why is it a misnomer? Because when you hear the term ridge, you think of something which is narrow, whereas these ridges present inside the ocean ridges, they are somewhat hundreds or thousands of kilometers wide. So, and one more thing that they noticed was that if you have ever seen a baseball, there are seams on the baseball which are connected to each other. Okay, so that is how they saw that. They said that these ridges, these are connected to each other all over the world oceans like the seams of a baseball. Okay, so this theory of plate tectonics, it began its idea from here after the Second World War. So now this, for the plate tectonics, Earth was divided into various plates. So now what are these plates? So these plates, these are the fragments of the lithosphere. Okay, so now when we did the structure of the earth with respect to physical properties, we divided it into lithosphere and asthenosphere, other than of course inner core and outer core. So lithosphere and asthenosphere. Okay, so while lithosphere is brittle and solid, asthenosphere, because of the certain temperature and pressure conditions, it is molten or plastic. So there is a weak zone that exists between the lithosphere and the asthenosphere, and on this weak zone, the lithospheric plates, they float. Okay, like ice floats on water. So now these lithospheric plates, we divided them into two parts: continental and oceanic. So the oceanic plates, they are denser than the continental plates. These were Sialic and Mafic, Sialic and Felsic, whereas oceanic plates were Sima and Mafic. Okay, so these were denser and these were lighter. Okay, so now these lithospheric plates, these are floating on the asthenosphere. So now the earth is divided into number of lithospheric plates. So there are 7 major lithospheric plates. So what are these 7 major lithospheric plates? Number 1 is Pacific, which covers the maximum part of which plate is covered by the Pacific Ocean. Second is North American, the maximum part of which is covered by the American plate, North American continent. Then South American, the maximum part of which is covered by the South American continent. African plate, the maximum part of which is covered by the African continent. North American, South American. Eurasian plate, the maximum part of which is covered by Europe and Asia, like China, Russia. They form a part of the Eurasian plate. Then number 6, you have the Antarctic plate, which is partly oceanic, and partly continental. So the Antarctic plate is partly oceanic and partly continental, and some part of it is covered by the Antarctic continent, which is the frozen continent, whereas some part of it is covered by the Antarctic Ocean. And 7th, you have the Indo-Australian plate. It is another major plate. It is a huge plate which is separated by various faults. So now, other than the major plates, you have certain minor plates, out of which 6 are important, and there are many of them, of course, but 6 are important. The 6 of these are also given in the NCERT. So number 1, you have the Cocos plate. So the Cocos plate is located in between Central America and Pacific Ocean and the Pacific plate. Second one is the Nazca Plate. The Nazca Plate is located between South America and the Pacific Plate. So when I'm using the term Central America or Pacific or South America, I mean Central American plates, and Pacific plates, South American plates and Pacific plate. Okay, and the Pacific plate. Then number 3 you have Philippines plate. Now where is the Philippines plate located? It is located between Asiatic plate and the Pacific plate. Then you have the Arabian plate. Arabian plate is the one which forms maximum part of the maximum part of Saudi Arabia. Then number 5 you have Caroline plate, which is located between Indian plate and Philippines plate. And finally, number 6, you have Fuji plate, which is located northeast of Australia. Okay. So these are the 6 minor plates which are important: Cocos, Nazca, Philippines, Arabian, Caroline, and lastly Fuji plate. Okay. So these are the minor plates which are present all throughout the surface of the earth. Okay. So what happened in this plate tectonics was that they said that while the places on the same plate, okay, they remained equidistant from each other, the places from different plates, they moved away. So like suppose when the Indian plate was moving, it was moving away from Madagascar. So the distance between India and Madagascar was increasing. Whereas if you see that the distance between the places on the Indian plate, suppose for example, say interior islands, say Bhopal and Indore, it remained more or less the same. Okay, so while the places within the plate, they were equidistant from each other, they remained equidistant from each other. The places on different plates, their difference between them were changing. They were moving away, moving towards, depending on the different type of plate boundary interactions, right? So now obviously the next question that will come to mind is, what are plate boundary interactions? So like I said, they could be moving away, they could be moving towards each other, the distance between them could be increasing, the distance between them could be decreasing, right? So because of that, based on that, there are different types of plate boundary interactions. Okay, so there are 3 types of plate boundary interactions, 3 types of plate boundary interactions. So what are these interactions? Number 1, you have a convergent interaction. You have convergent plate boundaries. Then number 2, you have divergent plate boundaries. And finally, you have transform plate boundaries. Okay. So what are convergent plate boundaries? Convergent plate boundaries are the plate boundaries that are moving towards each other. Divergent plate boundaries, as the name suggests, they are moving away from each other. And transform plate boundaries, they are moving past each other. Okay, so 2 plate boundaries that are coming together, convergent, that are moving apart from each other, divergent, and that are moving past each other like this, sliding past each other, that is known as a transform plate boundary. Okay, so these are the 3 basic types of plate boundary interactions. Now one thing that you should remember here is that all these plates that are there on the surface of the earth, these are basically a combination of there is different types of plate boundary interactions on the different borders. For example, there's a plate called John the Fuca plate. Okay, on the western margin, it is a divergent plate. Okay, on the eastern margin, it is a convergent plate, and there is numerous faults that are present within which form transform plate boundaries. Okay, so every plate, it is a mixture of convergent, divergent, and transform plates and transform boundaries on different sides. Okay, so now these are the three different types of plates. So now, like every theory, plate tectonics theory, it also has to be substantiated with good amount of evidence. Okay, like all these theories, they have to be substantiated by a good amount of examples. Like even for when we did the continental drift hypothesis, Wegener did give a couple of examples, right? He did, sorry, couple of evidences, right? He gave some 4 to 5 evidences. So when we are ahead of, we are now we are in the future as compared to the continental drift hypothesis. So obviously, there were theories, there were evidences which were given for the plate tectonic theory also. These evidences, they were based on the concept of geophysics, on the concept of radiometric dating, on the concept of magnetism. So we'll study them one by one. So first evidence that was given was, so the first evidence that was given for this was basically drilling. So different parts of the ocean were drilled, and there was a deep sea drilling project. Deep sea drilling project. What was this deep sea drilling project? This deep sea drilling project was basically a project which was a collaboration of many oceanic study institutes of the world, and they tried to drill the different portions of the oceans which were near to the ridges. And so what did they find when they began to drill? So the first thing, the first ship that began to start the drilling project was known as Glomar Challenger. Okay, so this was the first ship. This began drilling. It was known as the Glomar Challenger. Okay, so now what happened in this drilling? What they realized, that if this is the ridge, okay, or this is the portion where the new oceanic crust is being formed. So what did they find? That the sediments on both the sides of ridges, like if you see in this diagram here, this is drift, divergent, yeah. So you see this diagram here. Okay, so when you say the divergent convergent plate boundaries, what happens is, in the convergent plate boundaries, one plate goes beneath the other plate. So one plate is actually eating up the other plate. So that is a destructive boundary. When you say a divergent boundary, so what, like if you end up cutting your skin by some chance, blood will ooze out, right? So similarly, when you end up cutting the crust of the earth, magma oozes out. Okay, so now when there is a divergent plate boundary, what happens? The earth crust is cutting apart, it's moving apart, so magma will ooze out. This magma will solidify and form new crust, right? So these are constructive plate boundaries. Okay, so divergent plate boundaries, constructive plate boundaries, convergent plate boundaries, destructive plate boundaries. Okay, so now you see here, this is the asthenosphere, this is the lithosphere, and this is the region where the crust is opening up, or the ridge portion. Now what did they see in the drilling part? That this portion, the fossils formed here, and by the radiometric dating and everything, they found that this portion is of the same age. Then this portion and this portion, these are of similar ages. Then this portion and this portion are of similar ages. Okay, and then what is the next thing that they saw? That as you go from here to here and from here to here, the age is increasing. Okay, so what do we come to know from this? Obviously, this is the ridge, this is the main ridge. So on the two sides of the ridge, it is oozing out magma. So obviously, when it is moving away from each other, so the part that has been solidified, it starts moving away, whereas the new crust is always nearer to the ridge. And obviously, on both the sides, the magma that is oozed out in once at once will have similar ages. It will have similar fossils. The sediment over it will have similar fossils. Okay, so this drilling project, it gave them the evidence that there is a parallelism in the ages of the rocks that are found on both sides of the ridges. Second evidence, it gives them that as you move away from the ridge, the age increases. So obviously, when you're this is the part this so initially, see, this is the part of the ridge, okay, this ridge. So then it starts opening up, it opens up. So obviously, the part which was here first, it will move away, right? The one which was made first, it is pushed away. So the new part, it opens up. Okay, so this was the second evidence. Then the third evidence that they saw was that this part which is right next to the ridge, this area, okay, this highlighted area, it did not have very many sediments, whereas this portion, this region here, the part away, it still have some amount of sediments deposited on the oceanic on the igneous basalts, okay, on the basaltic rocks there were some sediments which were deposited. So again, what does it say? That says the thickness of the sediments is increasing, that means they are older, whereas this side also thickness is increasing, whereas on this side there were no sediments that were found. Why? Because this is just the new crust which is being created. So these were the three things that they found out. First of all, that there is a parallelism of the age on different sides. Second, the age increases as we move away from the ridge on both the sides. And third, this amount of sediments also increases as we move away from the ridge. So this was the first evidence that was given. Okay. Now the second evidence that they give was the evidence of hotspot. So the first evidence was for evidences. So the first evidence that was given was by drilling, and the second evidence that was given was by hotspots. So now what are these hotspots? So what happens at some places, the magma plume, it just begins to, it is so shallow that it begins to break apart the crust and move out, like for example in Hawaii. So what happens that here, see, so there is a magma chamber, that is magma is present here beneath the crust, and volcanism and magma comes out of it. So now if you know Hawaii, it is a chain of islands. Okay, the last one let's take for our lecture today as QI. Okay, and this one is Hawaii, the main island. Okay, so Hawaiian islands, they form a huge chain of islands. So what did they see? That the age of the different igneous rocks from QI to Hawaii, it was increasing from Hawaii towards QI. So now this is the part where active volcanism is taking place in Hawaii. Okay, that means the magma plume is here, the chamber of magma is here. So that means what would have happened, that the plate is, if this is the magma chamber here and here is Hawaii, here is QI. So what happens, what would have happened, that at some point of time QI might have been here, and with time it moved, the plate, it moved away from the magma plume and now it is under Hawaii. So that is why the age of QI volcanoes is older than Hawaii volcanoes. Okay. So this again was the evidence of sea floor movement, sea floor spreading, or the motion of the plates. Okay, so this was the second evidence. Now the third evidence is really really important, and it is the evidence of paleomagnetism. Okay, so to understand paleomagnetism, first you have to understand a couple of other things. So the first thing that you should know is that certain minerals are known as magnetic minerals. These are known as ferromagnetic minerals. Ferromagnetic minerals. So when these minerals, they are heated to a temperature known as the Curie's temperature, what happens is that they lose all their present magnetism. And when they begin to cool, they start getting magnetized again. Okay, so when they start getting magnetized, they arrange themselves according to the magnetic fields of the earth. So now if you have ever used a compass, you know that the needle of the compass will always point towards north. Why does that happen? Because earth is a giant magnet with a north pole and a south pole, and magnetic lines of force, they move from the south pole to north pole. So all the magnets that are present on the surface of earth, they try to align themselves with these magnetic lines. Okay, so what happens is that these ferromagnetic minerals, now the Curie's temperature varies for different minerals. For example, for magnetite, it is 585 degrees Celsius. Okay, so for magnetite, the Curie's temperature is 585 degrees Celsius. It varies for different temperature, for different minerals. The Curie's temperature varies. Okay, so what happens is that some ferromagnetic minerals, when they are heated to their Curie's temperature, they lose their magnetism. When they begin to cool, their magnetism comes back, and they begin to align themselves with respect to the magnetic lines of the earth. Okay, so now these are aligning themselves along the magnetic lines of the earth, so they will align themselves with the magnetic north and the magnetic south. Okay, so what happens is that with time, these magnetic north and magnetic south is basically somewhere closer to the geographic north and the geographic south, but not exactly the same. Okay, so this is how magnetism is found in a rock. So if a rock has been formed thousands of years back, okay, so now what will happen? That rock is formed so back in time. So the magnetism that it has, it is the, however it is aligned, it is the magnetism because of the whatever happened 1,000 years back, whatever melting happened 1,000 years back. So that magnetism is 1,000 years old. So it is a fossil magnetism which is present inside the rock. That fossil magnetism is known as paleomagnetism. Okay. So now, seeing this paleomagnetism, what did they see? They saw that here. So what did they see? That they saw that the different uh, rocks with different magnetic orientations, they are found in different orientations as considered. So different paleomagnetic minerals, they are found in different orientations in different periods of times. Okay, so what did this think? The scientists initially thought that okay, maybe what happened that the magnetic north and south of the earth, it must have migrated from its position. Okay, since it is not like the geographic north and south, it is not constant, it can migrate from its position. So if such different periods of magnetic north and south have been found, so obviously the minerals have aligned according to that, and they might have moved from their relative position. So now if you see this figure, so the alignment of the ferromagnetic minerals in different time periods has been shown for North America in the green and Eurasia in red. Okay, so sorry, Eurasia is in green and North America is in red. So this is the alignment in 100 million years ago. 200 million years ago it was aligned like this. 300 million years ago like this. 400, 500 and so on. So now what did the scientists say? Scientists said probably what happened, that north south of the earth was aligned like this 100 million years ago, aligned like this 200 years ago, aligned like this 300 million years ago. That is why these ferromagnetic minerals, they are also aligned like that. Okay, but then the discovery was made which said that there has not been a major shift in the position of the magnetic north and magnetic south. Okay, so what did they say? That if this is the present position of magnetic north and south, it has more or less remained the same throughout time. Okay, it has not moved much, right? So that means so much change cannot be brought about by only the movement of the magnetic north and magnetic south of the earth. So obviously what would have been the next explanation, that the plates which are carrying these ferromagnetic minerals, these might have moved. Okay, so that formed the another evidence for plate tectonics hypothesis, and later it was also given as an evidence for continental drift hypothesis. How it was given an evidence for continental drift hypothesis was that the plates, the areas of Africa, the eastern boundary of South America and the western boundary of Africa, they had similar types of orientations of the ferromagnetic minerals. So what did it show? It showed that they were at some point of time together. Okay. So that is how paleomagnetism, it became evidence for both plate tectonics hypothesis as well as the continental drift hypothesis. So revising it again, what happened in paleomagnetism, that different ferromagnetic minerals through their time, thousands of years ago, after they started cooling from Curie's temperature, they retained their old magnetism and were aligned along the geographic north and the geographic south during that period of time. Okay, whatever was the position of geographic north and geographic south during that period. Okay, so they were aligned according to that. Now what happened, that with the scientists saw that these old ferromagnetic minerals which have paleomagnetism, they have shifted their orientations through time. Okay, so now since they have shifted their orientations through time, there can be only two possible explanations. Either the plates which are carrying these ferromagnetic minerals, either they have shifted from their position, number one, or number two, these that these the geographic north and the magnetic north and the magnetic south of the earth has shifted its position. So first reason for this could be the polar wandering. It could be number one, that either the magnetic north and magnetic south of the earth has shifted quite a lot from its position, or second, if the probably the position of the plates has shifted, which were carrying the plates which were carrying these ferromagnetic minerals. So now with time, what did they find out? They find out that the position of the magnetic north and magnetic south of the earth has more or less remained the same. It has never varied way too much to cause so much of polar wandering. So then obviously the only explanation left was that the plate which is carrying these ferromagnetic minerals, it must have shifted. Okay, and this formed the evidence for both the plate tectonics hypothesis plate tectonics theory as well as the continental drift hypothesis given by Alfred Wegener. Okay, so this was the second evidence which was given. Okay, and this was one of the major evidence which was given, and this is basically the main thing. And other than that, radiometric dating was another evidence. So different rocks were dated, and then they found that the earth oceanic crust is not much old. It's none of it is older than 1 to 2 billion years, and whereas the continental crust can go up to 4.7 billion years. So obviously new oceanic crust was always subducted and formed, right? So these were the different evidences which were given for plate tectonics hypothesis. So now we have done what it is, we have done the evidences for it. So now we have to question ourselves that how this is happening, how it is happening. Okay, so now we have to do the mechanism for plate tectonics hypothesis. So coming to that mechanism for plate tectonics hypothesis. So for that we need to understand the concept of convection current. So suppose I have a big bowl of, I have a beaker of water and I am heating it with fire from below. Okay. So everything when heated, it expands. Everything when cooled, contracts. That's a basic law, right? So when there is water in the beaker, obviously the water here will be heated faster. So this water will expand. Once it expands, what will happen? Its density will reduce. So the water here, it expands and it rises. So let's take a different color. So the water here, it expands and it rises. This is hot water, it is rising. Okay. So now what will happen? The cold water which is present here, it will sink below and take the position of this hot water. Now this cold water that is sinking below will again rise and continue this cycle. So such currents are formed within the beaker of water. Okay. So this such currents where the fluid moves itself to transfer heat, that is known as convection current. So in convection current the fluid is itself moving. Now let's take this convection current to our mantle. Let's take this beaker example to the mantle of the earth. So what is happening in the mantle of the earth? This is the crust. This part is the mantle. So what is happening in the mantle? This is the core. So now core is generating heat, right? So this is the fire which is under the beaker. So this part of the mantle is hot. So this part is rising. This part is cold, it is settling down. So such convection currents are generated in the mantle. Okay. So these convection currents, these are basically the reason why the plates are moving away or towards each other. Okay, this is also known as the rising limb hypothesis. Okay, so these are the first, this is the reason why this is happening. So how are some plates moving away and how are some plates moving towards each other? That also we'll see. So now see, this is one convection current, this is another convection current. This is moving in this direction and this is moving in this direction. So now what will this convection current do? This will drag this plate, this part of the lithosphere, it will drag it away towards this side, whereas this will drag it away towards this side. So what will happen? With time what can happen? This will break and these two plates will start moving away from each other. So when they are caught between descending limbs or the limbs which convection currents which are moving in the opposite directions, the plates diverge away from each other. Okay. And how are some plates moving towards each other? Again you see this. The convection current is moving like this and this convection current is also moving like this. So while this is moving like this in this direction, this is also moving like this. So this will drag the plate with it. This will also drag the plate with it. So what will happen? Two plates will start moving towards each other. Okay. So this is known as the convection current hypothesis. Okay. So this is basically what drives the plate motion. So now there are certain forces that drive the plate motion. So what are these forces? It's given in the diagram here. Okay, probably I've forgotten to add it. Okay. So let's see here. What happens is the first force. Okay, first let's draw the diagram. So this is a convergent plate boundary where one plate is going beneath the other one. When we'll study the convergent plate boundary, we'll see how this happens, how dense a plate moves below. So here you have a ridge forming. This is a divergent plate boundary here. This is convergent plate boundary. These are moving towards each other. So this is moving here, this is moving here. So this one's moving here and this one's moving here. So now, so, like this, yeah. So this is the continental crust, this is the oceanic crust. Okay, so now you see this part of oceanic crust is moving down. So what will it do? It will try to drag the rest of the oceanic crust also along with it. So this mechanism is known as slab pull mechanism. Again, what happens? The oceanic crust is moving below the continental crust. So this slab is moving below to it's moving down from the below the continental crust. So it is so dense and so thick that it wants to drag the rest of the slab with it. So this is known as it's trying to pull the rest of the slab with it. So that is known as slab pull mechanism. So this is the most important mechanism which works, most important force, that is known as the slab pull mechanism. Now you see this is a ridge. Now what is happening at a ridge? Two plates are moving away from each other. So this ridge, it is trying to push it away. So this is known as ridge push mechanism. When at the ridge, obviously when the new magma is coming out, it will need place. So it will try to push the old plates away. So that is known as the ridge push mechanism. Okay. So now what happens? The third thing that happens is that at this boundary where there's convergence going on at the particular boundary, exactly where the slab is subducting beneath the other slab, what happens is that at that point there is a sort of suctional pull arranged. Suctional pull is there. Okay, what this suctional pull does is it tries to pull this plate also towards the subduction zone and this plate also towards the subduction zone. So this is known as slab suction. So there are three types of forces. One is slab pull, where the denser plate which is subducting tries to get the rest of the trailing slab along with it. Okay. And second is the ridge push, where the new ridge, where it is formed, it pushes the old parts away from each other, and that forms another mechanism force which drives the plate tectonics. And then the third one is finally the suction, slab suction. In that what happens at the zone of the subduction, what will happen that at the zone of subduction there is a sort of suction that is created which pulls both the plates towards the zone of subduction. So slab push, slab pull, slab suction and ridge push, these are the three mechanisms. Okay, these are the three forces. So now we all did the concept where we said that that the different convection currents are going on in the mantle. So now to explain these convection currents, certain models were given. Okay, so there were models given to explain these convection currents. So what were these models? We'll see that. So the first model that was given, that was known as, number one was known as layering at 660 kilometers. Okay, so now what had the scientists observed was that the magma that is coming out at the mid-oceanic ridges is different in composition than the magma that is coming out at hot plumes. Okay, so this is what they found out. So the first theory that was given was known as the 660 kilometer, layering at 660 kilometers. So what they said that this is the core, this is the crust, this is the 660 kilometer boundary, and here also you have the mantle, and here also you have the mantle. So according to this, what they said was that when the magma This is at boundary 660 kilometer. What happens is that there's a difference in the chemical composition of the magma, and this magma does not mix with each other. Okay, there is a immiscibility layer at 660. So what happened? They said when there is mid-oceanic ridge type volcanism, when this sea floor opens and you have sea floor spreading, so magma comes out from this region, the upper region. Whereas when hot plumes are concerned, the source of magma is below 660 kilometers. Okay, so these convection currents in the upper zone, they operate to these are helpful during mid-oceanic ridge type volcanism, whereas the convection currents from below, these are important for hot plumes or the hotspot volcanism. Okay, so this was the first theory. Now the second theory was this one, which was known as the whole mantle theory. So in this theory, as the name suggests, they said that what happens is that whole of the magma or whole of the mantle, whole convection currents are found like this. Okay, in whole of the magma. So now this is one magma, and what happens when a plate subducts something open, some other place, obviously somewhere the plate is subducting, so somewhere it is diverging. So there the pressure is decreased and the magma plumes, they move up. Okay, so this is known as the whole mantle theory. So this is known as the whole mantle theory. Now the next thing is the deep layer theory. This one. So this one is the most accepted one. So what did they say? They said that there are convection currents that are going on in the deeper mantle, and with those convection currents, there are swells and shrinks that are formed. So this is an irregular boundary. So at places it's swollen, at places it's shrinking. Okay, and these keep changing, swollen and shrunken portions, they keep changing their position. So what happens is that when there is subduction or when there is opening up of the crust, what happens is that because of the low pressure, this material, it might rise. So if it rises from the upper mantle, different type of magma is sent up, and if it rises from different part of magma is sent out. Okay, so there is no such fixed boundary. What happens is there is a deep mantle which is shifting its position, and there are swollen and shrunken areas, and these keep moving because of convection currents, and whenever there is an opening in the crust, magma might come out of the upper portion or the lower portion depending on the different chemical compositions of the magma at different areas. Okay, so to sum it up, what did we study? We studied that first of all, the convection current is the main driving mechanism behind plate tectonics. Driving forces are of three types: slab pull, slab suction, and ridge push. And there are three models which were supposed to explain the convection in mantle. So what are these three models? The first one is that it is the model called 660 layering model, which says that at 660 degrees there is a stability layer and different types of magmas exist. Then there is a whole mantle model which says the convection currents are flowing through whole of the mantle, and then finally you have a deep layer which says that there are swollen and shrunken structures present in the deeper mantle, and whenever there is pressure difference, the magma is buoyant and it moves upper to the crust. Okay, these are the three models. So now we have discussed the basic mechanism behind continental drift hypothesis, behind the plate tectonics, right? So the next thing that we are going to discuss is the different type of plate boundary interactions. So the first type of boundaries we'll do is we'll study divergent plate boundaries. Okay. So now what are divergent plate boundaries? So let's see here. So most of the divergent plate boundaries, they are found at, where are they found? They are found at along the oceanic ridges. Most of them, I said, not all of them. Okay, so divergence can occur. So either a ocean floor can open up or a continental floor can also open up, right? So either the ocean floor opens up or the continental floor opens up, right? So when the ocean floor opens up, you get mid oceanic, the features which are formed are known as mid oceanic ridges. When the continental floor opens up, you have rift valleys. Okay, so now let's see what happens when the ocean floor opens up. So this is an example. So mid-Atlantic ridge is an example of a mid-oceanic ridge. Mid-Atlantic ridge separates the North American plate from the South American plate, and Atlantic Ocean is there. Okay, so now you see here the North American, whereas the continent of North America is ending here, the North American plate extends till here. Okay, so now you see this is the mid-Atlantic ridge, it's a mid-oceanic ridge. So now what is happening, that this plate is moving here and this plate is moving here. So obviously when you cut the crust, what happens? Magma oozes out. So here at this portion you have volcanism, and these volcanisms they found, since it is a very buoyant and hot magma, this area is generally higher in altitude, some 2 to 3 kilometers higher than the surrounding area. Okay, so now in this region what is happening? In this region new crust is being formed, right? See, when magma comes out, it will solidify and it will form new oceanic crust. So what is happening? New crust is being constructed. So that is why I said divergent plate boundaries are constructive plate boundaries. Okay, so now that should clear your concept that why divergent plate boundaries are known as convergent plate constructive plate boundaries. Okay, so this ridge, it is higher and it has good amount of volcanism that is happening. And what is the volcanism that is happening? Basaltic lava is coming up. Okay, hence most of the ocean floor is basically basaltic in nature. So when we did in the in the previous lecture, when I told you about the ocean crust and the oceanic lithosphere and continental lithosphere, I mentioned that the continental one is mostly granitic and granodiorite, whereas the oceanic one is basaltic. So this is the reason why it is basaltic, because the lava that is coming out, sorry, is the basaltic lava. Now this is one thing, that it can happen on the ocean floor. Now what is the other thing? It can also happen on the continental floor, right? It can also happen on the continental floor. So these mountains that were formed in the oceanic region, they were mid-oceanic ridges, and as I have told before, the term ridge here is a misnomer, because what happens is that ridges, basically when you use the term ridge in geography, you think of something very narrow land, whereas these can go up to the thickness of even 4,000 kilometers. Okay. So now what is the next thing I told you, that continents can also separate and they can also form continental rifting can also be. So yeah, now you see this region here. What is happening? This was a hot mantle plume which was rising up. So because of this, what happened? There is a upwarping. What is upwarping? A domal structure, uplifting of the land. Okay, and these were moving away from each other, these plates. So in this upwarping, obviously as the magma rises, you will see volcanism. So then this continental plate, it breaks and the rift valley is formed. At this rift valley, you will see a lot of volcanism. Okay, so volcanism is seen. So when this rift further opens, like when the North America and the Eurasian plate, they were together. So what happened? Initially there was a continental rift. This plate, it broke. Okay, and there was initially a continental rift and a rift valley was formed. Then when it widened, it was filled with water, and then what happens? A linear sea is formed. And then after it further spreads. Now what will happen once this is started opening up? Basaltic magma will start to line up, right? So when new basaltic magma, it keeps lining up, and the rift valley keeps opening, it is filled with water on the top. What happens? It is formed into an ocean. Okay, so continental rift leads to the formation of ocean. Okay, so this process does not happen quickly. It happens over millions and millions of years. Okay, so that is how mid-oceanic ridges are formed, and through continental rifting. Initially, continental rifts are formed, and then with time, since the basalt keeps spreading in, mid-oceanic ridges are formed. Again, let's see it once more. What happens that the magma is rising, these plates are moving away from each other, so you have a certain upliftment and volcanic activity here. The crust opens up and there is continental rifting. Now, after the continental rifting, this small sea sort of area is formed, which is, and here you have the basaltic crust, this region. So, if you see in the diagram here, this portion which is shown in dark brown, this is the basaltic portion which is formed. So, a linear sea is formed, and with time, this basaltic portion it spreads on both sides of the and it forms the ocean crust. Oceanic crust is formed, and then the ridge between them is known as the rift valley. It is transformed into a mid-oceanic ridge, and the continents are moved separately to different sites. Okay. So that covers convergent plate boundaries. Divergent plate boundaries. So where is that example, as I've told you, the mid-Atlantic ridge. So now these ridges, these plate motions, they have different rate. Okay, while some can, the average rate we take it to be around 5 centimeter per year. Average rate of plate motion can be, if whether they are moving towards each other or away from each other, so it's 5 centimeter per year. But it can be as low as 2 centimeter per year, as it is in the mid-oceanic ridge, or as it is in the mid-Atlantic ridge, or it can be as fast as the 15 centimeter per year, as it is in the Pacific plate. Okay. So these can vary from place to place. Now, the next thing is left in plate tectonics is the convergent plate boundaries, the transform plate boundaries, and the various examples of these plate boundaries and the various features that are formed with these plate boundaries, which we will definitely cover in the next lecture. But for now, what is important, basic point of view is that you should be well versed with your atlas, especially the places which have been in news recently. So you should be aware of the places which are there in news. You should know what is there, why are they important with respect to geography, and why they are important for what type of questions can be asked with respect to geography. So the first and foremost thing I would like to suggest is that please buy a good atlas, be it Oxford, be it OBS, or any other brand that you like, but please buy a good atlas. Okay, so now the first thing that we have to study is latitudes, as I told you, which are important: equator, tropic of Cancer, and tropic of Capricorn. So a lot of times in a lot of exams, not just UPSC, many questions have been asked on which countries does the equator pass through. Okay, so the equator, it passes through many countries. So it started with, so we will be doing this in almost the end of every lecture. We will be making atlas entries. So first of all, we'll do something which is static, number one. So you can write atlas entries. Okay. Number one of the atlas entries is countries on the equator. Okay, so the countries through which the equator passes. So important is Ecuador, Colombia, Brazil. So these are South American countries. So after Brazil, you have Gabon and Congo, and then you have the important one is Democratic Republic of Congo. After that, it passes through Kenya, that is Uganda and Kenya and Somalia. So right now, Somalia is in news a lot. Why? Because there is a lot of pirates that are present in the area near the Gulf of Aden. So this country is very important country. What are the water bodies next to it? Okay, so then next important country is Uganda, Kenya, and Somalia. Okay, so now we've moved away from the African continent. So it passes through two important countries. One is Maldives, and other is Indonesian islands. So then you have 7, you have Maldives, and then you have Indonesian islands. Okay, so these are the countries through which the equator passes. Now you come to the Tropic of Cancer. So in the Tropic of Cancer, it passes through 8 states in India. It passes through Gujarat, it passes through Rajasthan, it passes through Madhya Pradesh, it passes through Chhattisgarh, it passes through Tripura, it passes through Mizoram, it passes through Odisha, states through which it passes in India. Okay, so again, if you open a political map of India, you will be able to see these states through which the Tropic of Cancer passes. Okay, so Gujarat, Rajasthan, Madhya Pradesh, Chhattisgarh, Jharkhand, uh, Tripura and Mizoram is through which it passes. So now another thing that has been in news recently is CPEC. What is the CPEC? CPEC is the China-Pakistan Economic Corridor. So what does the CPEC connect? The China to one part of Pakistan. So which part? The Xinjiang province in China is connected with the Gwadar port in Pakistan. Okay, so this is what it is connecting. Now, why does India have a problem with this? Because the CPEC is passing through a part of Pakistan. So this part where it is passing from is known as the Gilgit-Baltistan region. So there are some parts of India which are occupied by China, and some part of India which is occupied, some part of Kashmir which is occupied by China, and some parts of Kashmir which are occupied by Pakistan. So the parts which are occupied by China is in the eastern part of J&K, and that is known as Aksai Chin region. Okay, so that is known as the Aksai Chin region, whereas in the eastern part, the western part, the Gilgit-Baltistan region has been occupied by China. So now what happens is that this is known as the China-Pakistan. So if the CPEC it passes through this region, right? So it will give the world an impression that this part belongs to Pakistan and not to India. So India has a problem with this. India says that it is against the sovereignty of my nation. Hence, I will not support the China-Pakistan economic corridor. Okay, so it's actually part of the one belt, one road initiative. In the one belt, one road initiative, there are three things. There is a maritime Silk Route, which is a which is basically different ports that are found from China to Europe, okay, along the India. That will be the maritime Silk Road. Then one is the Silk Road. Okay, this the Silk Road, it passes through various countries, Kazakhstan and all, and it goes from China to Europe. And then last one is this CPEC, China-Pakistan Economic Corridor. Okay, so this is about CPEC. Now in yesterday or day before, there was a Koyna dam which was in news. Why was it in news? The Koyna dam was in news because from the Koyna dam they are releasing water for the Karnataka to overcome the shortage in Karnataka. Right. So now this Koyna, where is it located? It is located. The Koyna dam is located in Maharashtra. The Koyna river, it is basically a tributary of river Krishna. Koyna river, it originates at a place in Western Ghats as Mahabaleshwar, and it meets river Krishna at a place called Karad. Okay, so this is it. Also, there have been news about Satluj Yamuna linking project. So new Satluj becomes important, Yamuna becomes important. So we will discuss those in the next class. So for today, we'll end it here. Thank you.